My name is Valentina Betancourt and I'm going to be presenting Lab 2, Lines of Charge. First, an introduction to the lab. The purpose was to, in a similar fashion to our previous lab, look to develop a more sophisticated model for calculating the electric force on a piece of tape. We calculate the electric force on each smaller piece of tape using a model with many point charges on each piece. The experiment includes determining the force exerted by one piece of tape on another when they are measured a distance apart by creating two tapes, putting one across two books, and approaching an upper tape with the lower tape until the top begins to float. The reasoning behind this is we know ordinary objects acquire an excess positive or negative charge from simple interactions with other objects. Some key similarities and differences from the previous lab. In difference, we no longer treat a longer piece of tape as if it were a point charge, but rather we distribute the charge evenly across the length of the tape. In similarity, we assume that each piece of tape had about the same amount of charge. Expected results. When we approach two pieces of tape, we expect them to repel as they have the same sign charge. When approaching a piece of tape with a neutral object, we expect them to attract. And lastly, when approaching a piece of tape with a negatively charged object, we expect them to attract. Theoretical assumptions. First, we ignore air resistance on a moving object. Then, we also assume that both tapes have about the same charge, and each upper tape has about the same amount of charge distributed along its entire length. Initial measurements. The length of one piece of my tape was 1.9 centimeters, and the length of a fraction, which was 1/10, was 0.19 centimeters. The mass of one piece was 0.19 grams, and the mass of a fraction was 0.019 grams. The distance observed when the tape began to float was approximately 0.01 meters. For my measurements, first the magnitude of the gravitational force on tape B, calculated as mass times the gravitational constant, we achieved 1.94 times 10 to the negative third newtons. The charge on tape B I calculated using the gravitational force and setting it equal to the electric force. Plugging in the values and rearranging and solving for Q of B or charge of B, I achieved 4.644 times 10 to the negative 9 coulombs. For the corresponding number of electrons on tape B, I simply got the entire charge of my piece of tape and divided by the charge of one electron and got 2.89 times 10 to the negative 10 electrons. For the number of atoms on the sticky surface of the tape, I simply divided the length of my entire piece of tape by the size of one atom and achieved 1.98 times 10 to the 9 atoms on my piece of tape. For the ratio of the number of electrons to the number of atoms on the sticky surface of tape, I simply divided the last two values that I calculated and got that there was approximately 14.589 electrons per atom. The last calculation was the electric force on the floating piece of tape, which was equal to 1 over 4 pi epsilon naught times the charge squared over the distance when the tapes began to repel squared, and got 1.95 times 10 to the negative third newtons. Here is a first snapshot of my code. Here, this function called eField basically altogether calculates the electric force on the top point charge due to each lower point charge. In this case, I had 10 point charges as I divided my piece of tape into 10 smaller pieces. At the bottom of the code, we can see the loop that actually calculates this electric force. This part of my code highlights the other essential parts due to the blue arrows. The first blue arrow calculates the electric field at the location of each top tape due to the bottom. The second arrow shows the calculation of the electric force on the top tape due to the bottom. The third one shows creates the arrow for the net electric field at each top tape due to the bottom. And lastly, the last blue arrow shows the gravitational force vector on the entire piece of tape. Here is a snapshot of the output of my code. The red arrow shows the electric force vector, the yellow shows the gravitational force vector, and the white arrows show the electric force acting on each piece of tape. At the bottom, the output is the magnitude of the electric force and the magnitude of the gravitational force, and they are equal as they should be, so that shows that our results are correct. Lastly, some lab questions. First, if we had modeled the first question asks, what if you had modeled each of your tapes as a single point charge, like in the previous lab? First, I answered that we would have had less accurate results. For example, here, for the charge, we were able to get 4.67 times 10 to the negative 9 coulombs, as opposed to 5.67 times 10 to the negative 9 coulombs, which was what was achieved in the previous lab, which is less accurate. The second question asked, why do they differ, and which is more likely to be closer to the real value? I said that they differ because we are distributing the charge among the different pieces, which is more realistic than one single point charge, and therefore the line of charge method is more accurate, and the more pieces that we split the tape into, the closer we achieve the real value. A quick conclusion, we can conclude that we have achieved a more accurate result through this line of charge model as opposed to a point charge model, but still a point charge model was a relatively accurate simplification of the problem at hand and still achieved a good estimate of the amount of charge on the piece of tape nonetheless. Thank you so much.